Yes, sir.
If you observe very carefully, we have studied that elastic potential energy. So we can say that elastic potential energy is defined as energy possessed by on which body? Elastic potential energy. Yeah. Elastic potential energy is possessed by a what body, guys? Yes, which is only possessed by elastic body. So the energy possessed by the elastic body, in what way, everybody? Energy possessed by a elastic body in what
State
way?
of compression
Yes,
or
it is
expansion.
body by virtue of its. Yes, please. By virtue of its.
State of compression or
Yes,
expansion.
a state of
Compression or
compression,
extension.
a state of compression, and or what is that? Extension. Okay. So, for example, as I told you, if I am having a spring, if I compress it, in both the directions so that the size of the spring is reduced. Now the energy stored in the spring is what energy? Everybody. Now the energy stored in the spring.
Potential energy.
Elastic potential energy. Understanding? Now the spring is this much. This is compression. This is what we used to call as compression. Now the spring is this much. I elongated. The spring is very small. I elongated up to this much. Now you can see. So this much it is extended. That is what extension. So then now also the energy stored in this one. We used to call as what? Everybody. Elastic potential energy. So
Potential energy.
the energy possessed by a body due to the which body? Elastic body due to the what? By virtue of its state of compression or extension.
Extension.
That is what we used to call as, what we used to say, everybody? We used to call as
Elastic potential
Elastic
energy.
potential energy.
now.
Potential.
If you want to study the elastic potential energy, derivation of expression for elastic potential energy. So before that, we need to study a concept called as Hooke's law. Okay. And then after certain time, we people will go with the concept that is what expression for elastic potential energy. So if you observe elastic potential energy, so now let us derive the concept called as Hooke's law, one of the most important concept. So you never study anywhere, only now I am teaching you. Once you go directly higher classes, they will say directly only the formula. So that is what it is. So please all of you keep ready. So what is the concept we are studying now? All of you, we are going to study. Yes, please. Elastic.
Yeah.
Sorry, Hooke's law. Okay, so keep reading. Hooke''s. Hooke's law. Shall we start, everyone? I hope everybody is there in today's meeting. Am I right? Yeah. So that is what. So observe very carefully. So as it is very important concept. So formula also we are going to derive. So please make sure that if you have anything doubt, immediately you can ask me. Okay. So now let us see that, all of you. So Hooke's law means consider a wire of length L. This is length wire, guys. So wire it is, not a spring. Keep it in mind. This is called as string, not spring. String. Clear, Mare? It is a string. It is not a spring. Spring means, see, string means like this. Spring means what? Spring means like a coil. Is it okay, guys? This is called as spring and this is called as what? Yes, please respond.
String.
Spring. Now, I will introduce you two more things. The force which is exerted by a string, we used to call it as tension. What we used to call? Everybody? Tension.
Tension.
The force which is exerted by spring, we used to call as spring force. What we used to call? Everybody?
Spring force.
Spring force. Okay? So be very careful with that. Now, so for Hooke's law, for studying the Hooke's law, I'm saying you what I'm saying, everyone. Consider a wire of length who is having length how much? L. Okay. And area of cross section is A. What is the area of cross section of the wire? So I'm taking a wire of length L and area of cross section A. And you can see affixed to a rigid support. Affixed to a rigid support. This is what is our rigid support. What support it is, everybody? Rigid support. Understanding? Now, to the free end of the wire, a scale pan is attached. What is this pan, everyone? Yes, please. Scale pan. Beam balance theriyuma.
Scale pan.
Beam balance.
Yes.
That is only we used to call as what pan?
Scale pan.
Scale pan. What pan we used to call as? Scale pan. So, one end has to be attached to the rigid support. Another end, free end, has to attach it with what? All of you. Yes, please. Scale pan. Okay. Now, increase the weight in the scale pan in like a steps of 50 grams. How many grams? First, we have to put how much? Everybody. Respond, Raw.
50 grams.
50 grams. Clear, everybody? So, first thing, you should check it. What is the weight of the scale pan? What is the weight of the scale pan? We measured here. What is the weight of the scale pan? Weight of the scale pan. Here they mentioned it. Everybody see that.
W.
W. Clear? What is the weight of the scale
Sir,
pan?
W is weight, sir.
Yes, Mari. Weight of the scale
Yes,
pan.
sir. Yes, sir.
What is that, Emma? All of you? Weight of the scale pan. Clear? Now. So we have to conduct. You can conduct this activity and then you can see that. And you can see what is we have to increase every time how much mass I said, how much grams? 50 grams. Okay. So first you have to check it 50 grams. So that weight will become what? Total weight. W plus W. Understanding? So next again 50 grams you have to increase. Step 2. Next step. First one only W. Next one is W plus W1. Next one will become what? W plus 50 plus 50 equals how many grams? 100 grams. Next one again 50 grams. So that W become what?
150 grams.
150 grams. So this is what? Weight. So you have to increase the weight in such a way. How to increase the weight? First W, then W plus W1, that is what? 50 grams. Next W plus 50 plus 50, 100 grams. Next W plus 50 plus 50 plus 50, 150 grams. So every time 50 is increasing. And I have checked it before only scale pan. Now, as soon as I kept 50 grams, there is a change in the length of the string. Have you checked it, everybody? Yes, please. All of you respond. Yes or no?
Yes,
No.
sir.
What is the change
Yes,
in length? This is actual length, and because of weight, it has been extended some distance. That is what we are changing. Change in length always we can represent with what? Change. Change in velocity, change in momentum and all. We'll represent with what?
Delta.
Understanding all of you? Yes, please. All of you respond, everybody.
Yes, sir.
Yeah, now converting grams into weight. Ellame theriyuma. Mass into weight. Weight is equals to what? Mass into acceleration due to gravity. Understanding? All of you, please respond, girls, boys, everybody clear? Yeah. So first you should take only scale pan. After that, we have to put how much mass? Everybody? 50 grams. So that weight will become W plus W1. Then again 50 grams you have to add. So that weight will become what? W plus 100 grams.
Sir, why we are adding the weight, sir?
To see the elongation of that string. Understand, Mari?
Yes, sir. And how much it is withstanding.
Yeah. How much it is going to extend. That is what it is. Do you understand?
Yes. Yes, sir.
Purima? Yes?
Yes, sir.
Yeah. That is only we used to call it as actually the Hooke's law. That is why I am saying. Purima, Mari? All of you?
Yes, sir.
Yeah. So all of you observe. So original length is L. Because of putting 50 grams, there is a change in length. That is delta L. If I add one more 50 grams, definitely there will be little bit more. One more 50 grams, again extension. One more 50 grams, again extension. Definitely it will be there or not. Everybody, please respond.
Yes,
there will be slight change. So that change in length only we'll call it as a what? Everybody, please respond. The change in length we are representing with the what? This is original length and the new length is this one. The change in length only will represent with what? Everybody. Delta
Delta
L.
L.
So, all of you remember that this is only the change in length divided by original length. That is only we used to concept called as strain. What is to call, everybody? It is not English language, strain. Okay. So strain means change in length divided by original length. They will ask you to calculate the strain of a string or wire. Then this is the formula for calculating the strain of a string. What is the formula? Change in length divided by, what is this? Everybody, original length. So please write it. The ratio of change in length to the original length. Change in length to the original length of the wire is called, what is to call, guys? Everyone. Yes, please.
Strain.
Strain. Okay. So we are going to make spring constant. That's what Hooke's law. That is what we are going to make it now. So please remember that. Next. So if you notice it here, then there is another word called as strain. If your strain means, immediately what is that? Stress. So what do you mean by stress? Means the force acting per unit area. The force acting for how much area? Everybody. The force acting per unit area. That is only ways to called as stress. So can you tell me force by area something, another formula? Anybody?
Pressure.
You studied 8th class. Pressure is equals to what? Force by. Yes, please. All of you. Force by area. So that is only called as stress. So the force exerting for unit area is only called as stress. So please write it. So we are going to derive the Hooke's law, spring constant, force constant we are going to derive. So that is what it is. Okay. So please make it. So force acting per unit area is called, what is to call, everybody? We is to call as stress. So stress is equals to force by area. Strain is equals to, what is that? Okay, understanding formula? Strain is equals to change in length divided by original length. Pressure is equals to, yes, Abhirami, pressure is equals to, you can take it as a stress. That is what? The stress is equals to force by area. Okay, everybody? Mr. Mari, understand? Now.
Yes.
So if you observe, if you find out the, Lingesh, anything doubt you can ask me. If you find out the ratio of stress to strain, all of you understanding? If you find out the ratio of stress to strain, it is found that the ratio is a constant up to a certain limit. Up to a what limit? Certain limit. So that is what we used to call as elastic limit. As we are studying what energy now, everybody? What energy now? It is in a Laksha. Yeah, elastic potential energy. So elastic potential energy we are studying. So up to certain limit. So this the string cannot be continuously extended. Am I right or wrong? Everybody, please respond. So after certain extension, definitely if you put more weight, what will happen? Anybody can tell? If you put more weight after certain extension, yes, the string will break. Am I right or wrong?
Yes, sir.
Yes, all of you.
Yes, sir.
Yeah. So that is what. So up to certain extension, for example, I added 50 grams and I checked delta L by L. I found the strain and I checked the stress force by area. Next, I increase it to 100. Next, 150 to 200, 250, 300. So there will be extension up to certain limit. After that limit, that stress by strain ratio is not equal. That is not constant. So till what length you are getting the same ratio by stress by strain, that is what we used to call as, what limit we used to call as, everybody? Elastic limit. So means After that, is there any extra extension of the string? That is what I'm asking. Everybody?
No.
No, sir.
Sir, when the value of strain and the stress equals,
Yes.
that is known as elastic limit, sir.
No, Mari. Up to what? Up to certain limit, that ratio remains constant. After that, the ratio will varies. Means that is up to what length extension the ratio remains constant. That is actually the elastic limit. Do you understand? After that, it won't be extend. Clear?
Sir, then means the values of strain and stress will be same.
That's what. Values of strain and stress not. The ratio will be remains constant. Values is not Mari, it's ratio. If I divide the strain divided by stress, stress divided by strain, I'll get some value, some x value. If I divide by next extension, understand Mari? Now first delta L, then there is a change in length. Am I right? Again, I put 100 means definitely there will be extension. Correct or not?
Yes, sir.
For that, again, I will calculate the strain and stress. Again, if I do the ratio, again, I'll get the same x. That is what I'm saying. Up to certain limit.
Yes, sir.
That limit is only called as, what limit we used to say? Elastic. Yeah. Up to certain limits. Okay, Lingesh. Ratios are equal and values are equivalent. Whatever it is, Lingesh. So up to certain limit. That limit is only called as what? Everybody.
Elastic limit.
So,
Elastic limit.
that is only called as Hooke's law. What Hooke's law says that within the elastic limit, the ratio of stress to strain is constant. What is Hooke's law? Everybody? Within the, yes, please. Within the elastic limit, the ratio of what? Everybody? The ratio of stress to strain is constant. That is only called as, what law we used to call as? Everybody? We used to say that Hooke's law. Means in the sense of, from this, I'm giving chance to girls. Girls, can you tell me what is the relationship between stress and strain? As they both remains up to elastic, within elastic limit, both are remain, the ratio remains constant. Means both are directly proportional to each other or inversely proportional to each other. Agalya?
Inversely proportional.
Inversely, yeah. Oh, yo. How am I inversely?
So directly proportional.
So, as they're within the elastic limit, what is elastic limit, everybody? Up to the extension of his string, where stress and strain ratio remains. Where stress and strain ratio is
Sir,
what?
can you please say it again?
Yes.
Elastic limit means.
Elastic limit means, Mari. So, the ratio of stress and strain, if you keep on finding, so keep on, you will get constant. Up to what? After certain distance, after certain values, after 5-6 observations or maybe 6-7 observations, you will find that stress and strain ratio is not constant. So up to what last point, last observation where stress and strain is constant ratio, that is the maximum elastic limit. Do you understanding for a given string?
Yes,
That's
sir.
the maximum elastic limit. So that is only called as Hooke's law. Within the elastic limit, the ratio of stress to strain is always remains constant. Clear, everybody? All of you? All respond.
Yes,
so
sir.
now, so
Yes,
according
sir.
to that, you respond everybody. Stress and strain, both are directly proportional or inversely proportional to each other?
Directly
Stress
proportional.
and, yeah, directly proportional to each other. Ellame puriyuma, Kishore, Gokul, that is what. So from that means stress increases, strain also increases, stress decreases, strain also decreases. So that you're all very smart and we have studied already many things. Can you tell me how the graph will be? That is what is my question. If I draw the graph for stress versus strain, let me say, who will say you? Both are directly proportional to each other. Anybody? One increases, another one is also increases. Strain. Yes, please. This is A. Yeah. Sorry. Tell me how the graph will be. Anybody can tell. Both are directly proportional to each other. Both are directly proportional to Lingesh. Very good. Super Lingesh. Others. What is the expected graph? Agalya, Alfin, do you able to understand Alfin? Yes? The graph will be how, guys? Yes. Who is that?
Inclined.
Linear and inclined to the x-axis. Both are directly proportional. So they are linear graph. Stress and strain is always linear graph. Abraham is asking something. Sir, how, sir, they were directly proportional? Stress force applied divided by unit area. Strain change in length divided by original length. Ma, both are directly proportional to only. Ma, one increases only, another one. Both ratio is remains constant. Understand, Abraham? When you get a ratio, if suppose I will say pressure is directly proportional to force. Means in the sense of what? If I do pressure by area only, I'll get pressure by force only. I will get, sorry, force by pressure only, I will get area. Am I right, Abhirami? What does it mean? Both are directly proportional. Is it right or wrong?
Yes, sir.
Yeah, that's all it is I'm saying. Clear?
Yes, sir.
Yeah. So the ratio is remains constant. Means in the sense of stress and strain, both are directly proportional or inversely proportional. Everybody. Both are
Directly proportional.
directly proportional to each other. Now, if I do that, till here anybody having any doubt, you can ask me. All of you understand? Everybody? So how the graph will be? What is a graph?
Linear.
Linear graph. So remember. Okay. So now, let us form that. Now I will say the formula we are going to derive, Spring's constant, we are going to make it now. So Hooke's law will says that within an elastic limit, the ratio of what? Everybody. Within an
Stress and
elastic
strain
limit,
Stress and strain
ratio of
is constant.
is
Stress and
stress and strain is constant. Ellame puriyuma? Tanishka?
Sir.
Yes. Now, as I knows that mathematics, we can remove the proportionality. We have to bring something. What is that, everybody? Yes, please. I'll say
constant.
stress is equals to constant into strain. Am I right or wrong, all of you?
Yes, sir.
Yes. Then strain will come this side so that it will become what? All of you respond. Stress divided by
Strain is
strain.
equal to constant.
Equals to constant. That constant only I am taking as a E. What I am taking, everyone? E. So this constant
Elasticity.
we is to called as E is called as Young's modulus because it has been honor of Thomas Young. Because with the honor of what? Everybody? Yes, please. Thomas Young. So this E is called as with the honor of. Please remember. Honor of, in honor of Thomas Young. Thomas Young. Sorry. Thomas Young. So this E is called as what? The constant only what we is to call? Everybody. Please respond. Young's modulus. The constant is called as what?
Young model.
Young modulus. Okay. So this is what. So all of you observe when you elongate or extend or stretch a spring or the string, the force developed in it is directly proportional to magnitude of extension. So please note that point. So write that point also. When you elongate or extend or stretch a spring, right? When you elongate or extend, when you elongate or extend or stretch a spring, now itself I'm saying, if this Sunday I don't have a class for 10th in school, this Sunday will be the offline class. As the PT is approaching, this Sunday we are going to practice the chapter number 2, which is for PT2 syllabus. Do you all understand what I'm saying?
So when our PT2, sir?
Okay, sir.
Yeah. Most probably, I think after 10-15 days, we'll be having PT. So coming Sunday, if I don't have a school, mostly I don't have 90%, then the Sunday half day practice. Do you understanding? Sunday afternoon to evening, we are going to practice second chapter revision and as well as preparation for PT exam. Ellame puriyama. Everybody has
Yes,
to.
sir.
Yeah.
Yes, sir.
So when you elongate or extend or stretch a spring, the force developed in it. The force developed in it in it is found to be, experimentally found to be, directly proportional to the magnitude of extension. What do you mean by magnitude? Anybody? Magnitude means what? That number. Am I right or wrong? That delta L. Delta L means definitely there will be something 2 meters or 2 centimeter or 5 centimeter like that. This number is only called as what? Example I'm saying. That number is only called as what? Yes, please. This number only called as what, Ra?
Magnitude.
Magnitude. Understanding? So that is what. Sunday matudama. Okay. Saturday I want to take for 10th. That's why. So directly proportional to the magnitude of extension. So can you tell me mathematical relation for this? Anybody can tell? Force found that directly proportional to the magnitude of extension. Let take magnitude of extension is x. So that applied force is what? The force developed in it. Force is directly proportional to what, guys? Speak, guys. Directly proportional to
Magnitude of extension.
magnitude of extension. That is what? X. So F and X are what? F and X are force applied to the spring and the extension of the spring. F means what? Everybody?
Sir, we can find the magnitude of extension using the formula strain.
Yes, Mari, we can. That's what I said. I told you that formulas. Understanding? We are going to derive with the help of that only. We are going to find how much work done by the spring. That is what derivation for elastic potential energy. Like that only we'll find it. Clear?
Yes, sir.
Yeah. So what do you mean by F, everybody? All of you? F means what? Force applied to the spring. Force applied to the spring. Next, X means what? Extension of? Extension of the spring. Okay. So that is what you have to remember. So now, again, same thing. If I want to remove the proportionality, I have to take what? Everybody. Yes, please. I have to take something. What is that?
Constant.
Constant. So this constant only we used to call as elastic constant. What is to call?
Elastic
Elastic constant, or we can say spring constant. Please learn, everybody. Very, very important one. Spring constant, or you can say force constant. Your choice. So whatever you can learn it. Clear, everybody? All of you? Any doubt? Yeah. So if you draw stress versus strain of an elastic body, so the always you can see that the strain corresponding to the elastic limit of the body. So how the graph will be? Stress versus strain, everyone? Yes, please. Linear. Okay. So that is it. So please make it. So I hope everybody understand. Clear, everyone? Stress by strain is equals to Young's modulus. Okay. And F is equals to Kx. So K means what, everybody? What do you mean by K? All of you.
constant. Elastic constant.
Elastic constant, spring constant, elastic constant, or we can say what constant?
Spring constant.
Spring constant. Now, with the help of this, now for spring, for as well as string, both have been done. Now, with the help of this, we are going to derive the formula for what? Everybody? Yes.
Elastic potential.
Elastic potential energy. So derivation of, keep heading, derivation of expression of expression of elastic potential energy. Derivation of expression of elastic potential energy.
Potential.
So let's start now, everybody. So you can draw this diagram, all of you, so that you can make it very clearly. So all of you see that. So all of you remember, whenever it will attains the maximum elasticity, then we can say body attains equilibrium. What we can say, everybody? Body attains? What is that? equilibrium. Okay. So means further extension won't be takes place. That is a position we used to call as equilibrium position. Okay. So observe very carefully. Consider a spring of certain length suspended from a rigid support and block of some mass attached to it. So this is what you have to take the original setup. And if you leave it for some time, definitely there will be extension of spring. Am I right or wrong? Because of force of gravity. Am I right, guys? Everybody? Yes, please. All of you
Yes,
respond.
sir.
Yes. So that is what you have to remember it. So now you can take it here. So we are going to derive now formula for what, everybody? Elastic potential energy. Okay. So we have to consider a spring who's having a length L. Who's having a length L and some mass M is attached. And one is attached to the rigid surface, another side is attached to the mass. Free end. This is called as free end. So the free end is attached with the mass M. Okay. And it is going. Compressed, this is always for compressed also it is same. Understand, Kishore? Compressed or it is normal position. Purima. But this is A is the what? Actually, original length of the spring. What is that, everyone? All of you? Original length of the spring. No extension. So now, we do some work on it when we apply a force. So, when we apply a force means definitely what will happen? It will give something. Spring will react something.
Weight increases.
Yes. Weight increases or something will increase. It will give it an award. It will give an... What will give, guys? Because of mass.
Length.
Extension.
Extension.
It will give. So, work done on the spring from a state of 0. Actually, here work done is how much, guys? At this original length. Work done is equals to what? 0. Understanding? So, work done on the spring from a state of 0, extension to a state of extension. What is the extension length from here to here?
Sir, how did you found that the work done is 0, sir?
Here, no extension, correct, Mari? Displacement is 0 by the spring. Am I right or wrong?
Yes, sir.
Yeah, then displacement 0 means work done is 0 only, correct?
Yes, sir.
That is what. Understand?
Yes, sir.
Yeah. Remember all of you, when extension is 0, work done is what? Extension is 0. Work done is what, guys? Yes, please.
0, sir.
0. That is what you should remember. Understand? Speak, respond, everybody.
Yes, sir.
So when extension is 0, the applied force on the spring, F1 case. What is the applied force on the spring?
0.
K into...
0.
Yeah, we have got it. X. X is 0. So X is 0 means what is the answer? Applied force is equals to K into 0, which
0,
is how much? 0. Now,
0.
here there is a applied force, X. X. So that what is the force? X meters is the distance. So applied force, F is equals to what? Anybody? When extension is there.
Sir, length delta.
Yes. When extension, delta Venda, they have already taken X. So that what is the formula will come? F2 is equals to K into X, which is equals to what? Kx. Clear, everybody? All of you understanding? Yes? So whenever extension is 0, what is the work done? Everybody. Applied force is 0. So work done is equals to also what? Everyone?
0.
Okay. Whenever extension is there, what is the applied force? Speak loudly. Okay. Yeah, F2. Now, work done on the spring is equals to formula. I'll say you, please light it. Work done on the spring. Work done on the spring is equals to formula. Average force into total extension. Average force into total extension. Can anybody tell me what is the average force? You are all total extension. Average force, please. Average force. Average force is equals to, what is that? Hey, you are all mathematics students, right? F1 and F2, two forces are there. How to find average?
F1 plus F2.
Yes. F1 plus F2 by 2, which is equals to F1 is 0 plus F2 is Kx divided by 2. So what is the average force, everybody? Average force is equals to how much, Ra?
Fx by 2.
Kx by 2. Not Fx by 2. Kx by 2. That's all. So now you substitute it. Work done is equals to Work done on the spring is equals to, check it everybody. So average force. What is the average force? Kx by 2 into, what is the total extension? Check it. Here extension is 0 and here extension is how much? Yes, please.
Yes.
So the
Yes.
work done on the spring is equals to K into this 2 I will put separately. K 1 by 2 K into X into X. Everybody. X into X. Respond. X into X what, Ra?
X square.
X square.
2x.
So that is what? The work done on the spring is equals to what is hanging. So something energy. What is that? The work done on the spring is stored. The work done on the spring is stored in the form of some energy. Anybody? Yes. The work done on the spring. The work done on the spring is stored in it in the form of what energy, guys? In the form of
Elastic potential energy.
potential energy. So that, what is the elastic? EPE, elastic potential energy. Formula, anybody can tell me? Half into
1 by
half
kx
into
square.
kx square. X means what, Amma? K means what? Springs
Sir,
constant.
how did you wrote that? That's x square, sir.
Constant.
By
X
2.
into X, Mari. X into X square, correct, Mari?
Yes, sir.
X into X square, correct?
Yes, sir.
So what is the elastic potential energy, everybody? Half into springs constant into X means what? Extension. X means what?
Extension.
Extension. X square. Remember, compression also same. Compression means what?